often have large bias between things that seem aesthetically scientific, meaning they use words and phrases that sound scientific, and things that don't. With the right language, anything can be made to sound authoritative. What makes something truly scientific then? An idea or a practice isn't scientifically supported because it was developed in a lab. Rather, it means that it has been studied empirically through an experiment with defined terms and parameters. In short, it means that whatever claims we are making about it, we have a clear, logical, and reproducible evidence to say so. What this means is that anything, even something we think of as superstition or folk tradition, can be understood through a scientific lens. Many traditional practices, such as Chinese acupuncture or even chicken soup to deal with a respiratory infection, when tested and analyzed scientifically, we're better able to understand why they are useful and maybe find ways to better use them. Just as it's important to see through pseudoscience and false claims, we also need to not write off something because it doesn't dress itself in scientific language. Being scientifically literate allows us to better use the knowledge that comes through the human experience and then put it to better use. Our diet and food habits are very important to understand scientifically, because the food that we eat contains the essential nutrients which our body needs for normal functioning. Diet and food is one of the most basic ways in which we can affect our health and well-being. Hence, we should give some attention to it. And how do we do that? We need to understand it from a scientific perspective. Diet and pseudoscience have great affinity for each other, and that's unfortunate. Why is that so? Diets are very personal choices, and a lot of times the food that we eat is very tied to our identity as a race, our identity as a person. These are compounding factors that will come in when we are trying to study whether diet A or diet B works better. And when these compounding factors are not controlled, the results that emerge is very difficult to generalize. As such, most diet studies are correlational in nature rather than empirical in nature. And because it is correlational in nature, its reproducibility and generalizability are limited. When it comes to diet, I think what science can offer us are suggestions, good principles that we can actually utilize, rather than hard answers like this is the perfect diet for everyone. Simply because in diet science or in food science, contextual factors are extremely important. So for a study that is carried out, there are specific contextual factors which are taken into consideration. And when you try to remove the finding from its context and apply it to a new context, you may not actually get the same effect or the same results. Just because something works in one context doesn't mean that it will work in all contexts. One diet that's become quite popular in recent years is the ketogenic diet. You might have heard of it as the carnivore diet. Basically, it involves you avoiding and replacing all but 5 to 10% of your carbohydrates. Instead, your food intake is concentrated proteins, fats, and high-fiber vegetables. It's become quite popular as a means to help with weight loss, diabetes, and even prevent epileptic seizures. But when you Google it, you can easily find a large amount of articles saying both it's good and bad. How do you really decide if it works or if it's just a health risk? Again, let's turn to peer-reviewed studies. They are really the best tools for finding verified evidence. But like any other tool, we really need to understand how it works best and its limits. There's basically 3 kinds of scientific studies. The first kind is empirical studies. Empirical studies are those that actually happen within the laboratory setting under controlled conditions. An example of an empirical study that can actually be carried out in the laboratory say we want to find out whether different combination of light color would affect the rate of photosynthesis. So what we would have done is we would grow seedlings, and then in the laboratory, we will have controlled temperature, controlled humidity, but to subject them to different light conditions. Over a fixed period of time, we would measure the growth of the plant. So you realize here that the conditions are all controlled except for the color of the light that we are exposing the plants to. The second kind of study are correlational studies, simply because not all studies can be empirical in nature. So in correlational study, we don't actually carry out an experiment and get the data from the experiment. For instance, it's very familiar to us on cigarette packs that you say smoking causes lung cancer. So the question here is, how did we come up with that conclusion that smoking causes lung cancer? Was there any empirical studies that was carried out? Obviously, the answer is no, right? Because you will never get clear ethics and there will be no volunteers because you can't possibly get 40 volunteers and say, come, I'll lock you up in a room and I'll feed you cigarettes for the next 20, 30 years and you smoke 10 a day and we'll see if you die from lung cancer. That never happened. So there is no empirical study or data that's available for us to conclude that smoking causes lung cancer. But that particular one came from a correlational study, meaning that for every person who died from lung cancer, we trace their life history. And we can possibly say the lung cancer was probably caused by smoking. So we use the statistics to make a deduction. The third kind of scientific studies are modeling. So in modeling, we actually don't conclude with existing data. We use past observations or past trends. We put them into a computer system, we make certain hypotheses, and they will generate a model for us to say, well, based on past data, this is likely to happen. So take, for instance, the billion tree project around the world. We say that if we plant 1 billion trees, we will be able to reduce the rate of climate change. Have we planted the billion trees yet? We haven't. If we haven't planted the billion trees, how do we know? How do scientists know that by planting 1 billion trees, we will be able to reduce the rate of climate change? We know it because we did some mathematical modeling based on existing rate with which carbon dioxide is being produced into the air and at the rate that most trees would have photosynthesized under the current conditions of our climate. We did some mathematical modeling and then the mathematical model predicted that if we were to plant 1 billion trees, we would be able to reduce the rate of climate change. So here we have 3 different kinds of scientific studies, and whichever scientific studies you are reading up on, you need to know where the limits are and what the potentials are. Scientific studies are typically guided by research questions, and research questions are specific in nature because the scientists themselves would want to find out and be able to carry out experiments to show a specific phenomena. With each experiment, we show a certain physical quantity or a certain variable, how it changes when we change other conditions. So most of the findings are specific to answer the research question. So is the keto diet good for us? Does it have some real benefits for us? Let's take a look at some studies. This study, for example, looks at the effect of ketogenic diet on preventing epileptic seizures in children. It has a pretty large multi-trial sample size, which is good, and it has a very specific criteria to measure whether a seizure in any given patient decreases when on the diet. This study concludes there's a clear correlation and the diet does work to stop seizures. And this study looks at the effect of a keto diet on people with type 2 diabetes and whether it is helpful in weight loss and stabilizing the level of glycemia in the blood. Again, it has clear and repeatable experimental model, and from that, very definable results. Its conclusion? That it did help control glycemic levels in subjects and did help weight loss. It seems to at least correlate with the idea that this diet offers real health benefits. And this study compares a keto diet with meat to a similar low-carb diet, but with all vegetable and no meat. It studies their effect on weight loss and blood pressure within the test group. Now, the interesting thing here is that, again, the keto diet is showing healthy, effective results. However, The vegetarian alternative is showing even better results when it comes to the same outcome. So while this might start to answer some questions we have about the diet, it certainly raises a number of others. Science cannot answer all the questions in the world. There are limits to what science can do. First limitation of scientific studies is that we do not want to overgeneralize the findings of specific studies. When scientists design a specific study, they have a context in mind. When we take the results and want to apply to a new context, we also need to take the different contexts, the differences in the context into consideration. The limits of science also comes from the fact that science is unable to answer questions such as, how does life on Earth begin? Science cannot answer question, is there God? These are things which are not observable, which we cannot collect empirical data, and therefore we are unable to answer these questions as scientists. In order for science to tackle big questions, we need to rely on multiple studies. Results from one study will feed into the next study, and then we find out more, we will then feed it into yet another study. It's like a snowball effect. As the snowball moves, we collect more and more evidence, we collect more and more data until we get to a point where we are satisfied with the answers that we have obtained. Scientific papers are usually written for specialized audience, scientists, practicing scientists. So within the community, they speak the same language. And a lot of times, the scientific papers are written in very complex language, using very specialized vocabulary. So the question, of course, has been asked, why do we need to have specialized vocabulary in scientific papers? Now, science tries to capture very abstract ideas and communicate them. Now, a lot of times our lay language fails to capture the complexity of the phenomena in science. We have to invent new words to try to have these meaning packed inside science. Let me give you an example. When you see a car along the road, a lay person would probably say the car moves faster and faster. A scientist would say the car accelerates. Now, the term acceleration packs within it a change of velocity, which means a change of speed and direction. So sometimes the lay language fails to capture complex ideas, and that's why we need to have specialized language. So science is always perceived to be inaccessible to the layperson because of its scientific language. And that is why this whole movement to bring scientific knowledge to the lay community has become increasingly popular. We are talking about getting science writers to translate complex ideas into forms which people can understand. The more we make scientific knowledge accessible to a wider audience, we will realize that there are actually many people out there who are interested to find out more about science. So science is not just for scientists. Science is for everyone, that we can actually make sense of the science that is out there so that we can make sense of the world around us. Scientific literacy encourages people to see how relatable and applicable it is to our own lives. And we start to focus on how the right information can change our lives for the better.